Today we have this problem. We are going to determine the electrical field due to an infinite planar charge with uniform charge density, ρ. Okay. In this problem we have this piece of an infinite flat sheet where the charge is uniformly distributed upon it, which means that each point on this plane has the same charge density, ρ. We want to determine the electrical field caused by this plane. Okay. We are going to use Gauss's law. We know that Gauss's law is stating that Gauss's law stating that the net outward flux of the electrical field through the Gaussian surface is equal to the total charge enclosed in this surface divided by the permittivity of the free space in our problem exists in the free space. Okay. So easy to find that the electrical field due to this plane is going to be perpendicular to this face. It's going to flow in a perpendicular manner to this sheet. So the electrical field is going to flow upward. Okay. In this case, the vertical axis is z-axis. So for the top face of this sheet, for the top face of this sheet, we have the electrical field for the top sheet, which I am going to represent by T subscript. Okay, ET times the Gaussian surface homogeneously to Gauss's law equals the electrical field is flowing upward. So okay, and now regarding to the Gaussian surface, each point on the Gaussian surface must have the same distance from this sheet. So this Gaussian surface can be something like this. Okay, I assume that this box which stands on the top surface of this plane, the Gaussian surface that we consider in this problem is this manifest surface. This surface will have some arbitrary area which is A. Okay, and of course according to Gauss's law, this differential surface is a vector. So this surface must be vector, and we know that the vector of this surface is perpendicular to this surface. So it's perpendicular towards the direction. Okay, dot is it RDS. Okay, and the same thing is the integration. Okay, and the answer of this integration is going to be these unit vectors is going to be eliminated because the dot product between the unit vectors is 1, and this is constant, so we can take it out of the integration, and the answer is going to be AZ. There's no bar up there. AZ times DS. Okay, and this is for the top face. For the down face, for the bottom face, I mean. For the bottom face, the electrical field is going to flow downward. It's going to flow toward minus AZ direction. Okay, and also the Gaussian surface is going to be like this surface, but it's beneath this sheet. It's something like this. Okay, I hope you see it. Okay, and the Gaussian surface that we considered is this surface. You see this area which has the magnitude of A. Okay, and the unit vector for this area is intuitively towards AZ. So for the bottom face, the electrical field I'm going to use B subscript, which denotes to the bottom. And do the dot product, and the same answer is going, and we will retrieve the same answer. Okay. Now, in order to apply this Gauss's law, we are going to add these two distributions before adding the right-hand side. Okay, so we are going to add these two these two contributions, and the answer is going to be, the answer of the summation is 2az equals, okay, Q is the total charge enclosed in this area, in this Gaussian surface, okay? So the total charge enclosed is equal to the charge density, or the charge per unit area, times the area of this surface. It's rho sub s, which is the charge density, times A, divided by epsilon. Okay, now do this integration, and the answer is going to be S, and we are going to substitute S for A, so the answer is A for this. So now we are going to substitute these to the other side. I'm going to write the rest of the answer on this part, on this empty part. By dividing both sides by 2a, the answer is going to be, okay, this is the scalar component of the electrical field. Now, the electrical field for the top face, or the electrical field when z is greater than 0, okay? Intuitively, the electrical field is going to direct vertically upward. So the electrical field is going to be, we are going to only add the unit vector A sub z. And for the bottom face, z greater than less than 0, the electrical field is going to direct downward. This is the final answer. I only rewrote this on a new paper, a new neat paper, and that's the end. See you in another video.